Our first speaker is Octavio Arizmendi from CIMAT. He obtained his PhD at Salem University in 2012, and since then he's a professor at so he's going to talk about free probability, random matrices, and polynomial convolutions.
So thank you very much, and thank you very much to the organizers for giving me the opportunity to present my work at this very nice conference. So I was a student. When I came to, I guess, 2012 to the Symposium, and I found it very interesting. So I'm very honored that now you decided that my research is good enough for students. So I will talk about free probability random matrices, and also about something called finite free probability, or also called polynomial convolutions. And the last part is a joint work with Daniel Perales, who is a student of the Master's in Probability and Statistics in CIMAT. So I should apologize to the people who were in the Mexico-Poland meeting, because this talk will be very similar, but there will be at the end some new things. Hopefully these 5 minutes will be interesting enough for them to hear the whole talk again. So I will talk first about free probability, then about asymptotic freeness. Then I will explain what is finite free convolution or polynomial convolution. And at the end I will explain the results with Daniel about cumulants in finite free probability. So let's start. So what is free probability, or more generally, what is a non-commutative probability space? So the idea is that we take an algebra and a linear functional, which sends the identity of the algebra to so this linear functional goes from the algebra to the complex numbers, and it sends the unity of the algebra to 1. So here we should think of tau as an expectation, and of A as the set of random variables. So we are forgetting somehow the sigma algebra, and we're just looking at functions on the sigma algebra. And this is what we will be interested here. So for us, random variables are just elements of my algebra. Real random variables are elements which are self-adjoint. So to talk about real random variables, I need to add an involution. And if I want to have probability measures which are real, supported on the real numbers, I need to talk about positivity. Positivity means that positive elements, that means elements of this form, A star or A star A, are sent to a positive number, well, non-negative number. And the framework that allows that we work with normally is C-star algebras. And if I work with positive functionals on a C-star algebra, then I can be sure that I have a distribution. So what is a distribution for us? So here we only have a functional and random variables. So somehow the information of a random variable or its spectrum is given on how tau acts on powers of my random variable. So this is the expectation of powers will be called moments. So the kth moment of my random variable is just tau on a to the k. And in fact, if I'm in a C-star algebra and this functional is positive, this Rees representation theorem, which can be generalized broadly. So in general, Rees representation theorems tell me about a sign measure, but if it's positive, then it is a probability measure. Why is it a probability measure? Because I am putting in my non-commutative probability space, I said that tau of 1 is 1. But if I put in the left-hand side 1, sorry, 0. Sorry, in the right-hand side, 0. I will have here 1, and in the left-hand side, I will have the total mass. So that's why I need to send tau of 1 to 1. So then I can talk about distributions and about moments, and this will be how I can do probability in this framework. Okay, so examples. The first example comes from classical probability, and here I should strengthen the fact that we are forgetting about many things. So for example, we don't have paths. So when we talk about stochastic processes here, we don't have paths. We don't have distributions at time t. Right? So we're losing things, but still we can recover distributions. So for the first example is if I have, say, bounded real random variables, so that the distribution is determined by moments, then I can extend this to complex random variables, and this is a linear functional which satisfies these properties that I mentioned. It means it's positive and sends 1 to 1. The other canonical example is, of course, random matrices. But before going to random matrices, I need to tell you how to do matrices. So matrices is, so I have my set of matrices of size n, fixed n, and then I consider the normalized trace. So the normalized trace is just the trace divided by 1 over n, and I should do this because I want to send the identity to 1. So the trace of the identity is n, so I use normalize, and this gives me a positive linear functional, because the trace of matrices which have positive eigenvalues is, of course, positive. And so I can associate a measure to each of my matrices. And I combining these two, I can make the space of random matrices. In fact, I can say the space of matrices over any algebra 1. And I just combine the two functionals. So I take the expectation on each entry and then take the trace of this matrix, or either I can take the trace, which is a random variable, and then take the expectation of this. And this is a non-commutative probability space, which is also positive and sends 1 to 1, because here identity, of course, is the identity in the matrices. Okay? Okay, and how do the distributions that I defined before look like in these examples? So in the first case, what we get is, of course, the usual distribution, okay? Because the distribution satisfies that the nth moment is exactly the expectation of x to the n. In the second case is what is called the empirical spectral or eigenvalue distribution of a matrix, and this is the measure that gives weight 1 over n to each of the eigenvalues. Okay? And then the question is, what is, in the third example, the distribution that I defined before? Okay? So the distribution is defined by the moment formula that I gave you before, and it is explicitly calculated in this form. So what you do is just take the empirical distribution and integrate over the space. Okay? And this is called the average distribution, and here it is important that this is not a random measure. This is a fixed measure, which is somehow the average of the empirical distributions for any omega. Okay? So if I have a measure, then I can talk about convergence in distribution. And typically, in many examples, what is studied is this one, and then this random measure, which is taking any omega, is proved to be very close to this one when n is very large. Okay? So let me give you a very different example, which is really algebraic, which is the group algebra. So the group algebra of any group, which is, say, discrete, is just formal sums of elements of my group multiplied by some coefficients in any field. In this case, I'm taking the field to be the complex numbers, and then I multiply like following the rule of the group, and I consider the functional which sends to each sum I only consider the element, the coefficient of identity in the group. So here is the identity in the group. So in other words, what I'm doing is I send it to the elements in the group, I send it to 0, or if this element in the group is not the identity. And I'm extending linearly. Okay. Sorry? Sorry, phi is tau. There was a mistake here, sorry. Tau is phi. Okay. And here you will maybe think that maybe this many information is lost. But again, as I mentioned, if one takes powers of my elements, somehow I can recover a lot of information on who was this guy. Okay? And this is the idea. I not only need to look at the expectation of this guy, but expectations of all the powers. Okay? So then one example which is very important is the free group. So the most simple group that you can imagine given two groups, how to construct another group. Of course, the most simple is to take the commutative free group, but we don't know about this here. We just do a more simple construction. What we do is just concatenate elements in the group from the first group and in the second group. So I need to tell you how to multiply. Well, multiplication is just concatenating, and then if I get two guys which are in the same group, I just multiply them. So here, an example, there is some cancellation. So A and A minus 1 cancel, B and B minus 1 cancel, and get A to the fourth, and the rest is just the same. Okay? And there is this observation that if I have two groups and I consider the free product of groups, for any element AI, here AI is not in A, but is really an element in the group algebra, so a sum of formal sum, and B is in the second algebra, group algebra generated by G2, then if these two guys have mean 0, meaning that in this means that in my sum, in the coefficient of the identity, this is 0, right? So you see, if I multiply two of these guys, since there is no relations, there's no way to get another coefficient for the 0 element, for the identity element. So what will happen is that if I have alternate products of elements in G1 and G2, then the product will be also have mean 0. Okay? And in fact, if I know this rule, so this is an if and only if. So two elements in this big group are free algebraically, if and only if they satisfy this rule. Because if there is some relation between them, then I will find some polynomial that gives me something in the identity, and this won't be 0. So this is a theorem, but also this is a motivating example to define free independence. Okay? So Voiculescu defines, in fact, for any two algebras which are contained in a bigger algebra, so we say that these two algebras are free with respect to the functional tau if for any elements which alternate, sorry, for any elements which vanish with respect to tau, the product of alternating elements is also vanishing. Tau of AI here, sorry. Okay, so how should I understand this? I should understand this. So maybe it's a little bit strange at the beginning, but this is like a rule to calculate mixed moments. Mixed moments means how to calculate tau on products of random variables on two variables. Okay, and this will give me, in fact, the distribution of the sum or the product or many things, provided that I understand correctly this formula. Okay, and in fact, this theory is very rich. We can talk about central limit theorems, infinite divisibility, stable laws, Levy processes. Here again is in the distributional sense, Gauss expansion, stochastic calculus, etc. Many things. Okay, And let me just tell you what is the central limit theorem here. So the central limit theorem is same conditions as in the classical central limit theorem, but instead of assuming that they are independent, they are identically distributed, but they are free. What I mean free is that they are free independent. This means that they satisfy the relation I mentioned before. And what happens is that if I add them and then normalize, what I get here is not the Gaussian, but I get the so-called semicircle distribution, which is like a semicircle in -2, 2, just I need to make it a probability measure. Okay, so it should be the elliptic distribution. Okay, and if I want to work with measures, then I can define the free convolution, which is just if I have a measure, the measure of A, the distribution of A and the distribution of B, then I call the distribution of the sum the free convolution. And of course, this doesn't depend on A and B, so I can just forget about the realization. And I can do similar things for multiplication, which is the so-called free multiplicative convolution. And this is the symbol. And I just need to take care about positivity, because if I want to take a measure, a positive measure, I want this to be self-adjoint. So instead of taking A times B, since here things do not commute, I need to take this other element. But this element has the same moments as A times B. Okay? Good. Okay, so how do I calculate free convolution? So free convolution, to calculate free convolution, I instead of looking at the Fourier transform, I look at the Cauchy transform. So this guy is an integral over the measure of 1 over c minus x, but should be understood as the expectation of 1 over c minus a, where a is my random variable. Okay? So instead of taking e to the tx, I take this guy. And it happens that if I take the inverse on their composition and subtract the pole at 0, this linearizes free convolution. Okay, so the rule is I take this guy, then I take the inverse, then I add, take one pole, then I add, and then to come back to this, then I do add the pole, take the inverse, and then get the Cauchy transform. From the Cauchy transform, there is an inversion formula to get the original measure. And you will see here that the main problem to really calculate these things is that I need to take an inverse. And this is really a problem, but it has been solved at least numerically. Okay? There is a similar theorem for the transform for multiplicative convolution, which I won't talk about this before. Okay? But here I want to talk more about the combinatorial approach. And the idea is that I want to talk about what is a cumulant. So cumulant for classical convolution was defined, in fact, more than 100 years ago by Thiel, but free cumulants were defined maybe in the 80s. Okay, so what should cumulants satisfy? First, I need to recover cumulants from moments. So I should have the same information. And this is this property 1. So this is a polynomial in the first n moment with leading term, my nth moment. Here mn means tau on a to the n. So this ensures that I can recover kn from mn and mn from kn. Second is that it should behave nicely with respect to multiplication with a constant. And since this is of order mn, it cannot be homogeneous, but it's homogeneous of order n. So it means lambda goes to lambda to the n when factorized out. And finally, and this is the most important thing, is that if I have two independent random variables, and here independent means any independence, like if I talk about classical independence, this is one cumulance. I talk about free independence. This is another cumulance, and there are other notions of independence, and this notion makes sense. Okay, so of course one question is first if they exist and if they are unique. Uniqueness is proved easily, and existence could be proved provided that you have an R transform. Because if you take the coefficients of the R transform, since the R transform satisfies this property, the coefficients also satisfy this property. And this is the approach of Voiculescu that I will explain later. Okay, so why should I care about cumulants? Maybe one way is by an example. I can prove the central limit theorem with these cumulants, just with these properties. So the proof is very simple. Here, this is a mistake. This should be n to the 1/2, of course. Okay. So I take the sum and the normalized sum, and I want to know how the cumulants behave. So since I am assuming that mean is 0, then the first cumulant is also 0. And I assume instead of saying that the variance is 1, I will say that that the second moment is 1, I will say that K2 is 1, which is in fact the variance. So anyway, so I calculate first the first cumulant. So I sum these guys, and since if each of these guys is independent from the other ones, it's just the sum of the cumulant. And since each of the guys has a cumulant 1 equals 0, I use the last property, so this should be 0. Okay, then I go to the second cumulant. So the second cumulant, I have the same property, but here this n, since this is the second cumulant, this n to the 1/2 goes away out as n. Okay, and then I have n terms, right? And then this n with this n cancels, so the second moment is 1, just like as in classical probability. And what happens with the largest one? Well, it's the same thing, but here instead of having n to the 2/2, I have n to the n/2. And as long as n is bigger than 3, this will go to 0 as n goes to infinity. So in fact, this is a proof that I give sometimes to my students, even in classical probability, to show the central limit theorem, assuming that we have all moments. Okay, and the same holds for free probability. But you see, then I need to know what's the relation between moments and cumulants. And there are two approaches. The first one, as I mentioned, was by Voculescu, and he says definition. The free cumulants are the coefficients in the expansion of the R transform. Okay, so this is proof of existence and uniqueness, but somehow doesn't tell me a lot on what is the limiting distribution. I only know that the limiting distribution is the one whose cumulants are 0, 1, 0, 0, 0. However, Speicher showed that the underlying combinatorial theory of cumulants is described by non-crossing partitions. So this is the so-called moment cumulant formula, and if I change non-crossing partition, so I should tell you what is this formula. So what I'm doing is first summing over non-crossing partitions. So a partition is just I have n points, okay, and I divide in subsets. For example, here I can have so I have the subset which are called blocks 1, 4, and 7. Then 6, 8, and 2. 6, 8, and 2. And then 3. Okay? And as you see in this picture, this, can you see? Sorry? 5 is alone again. 5. Thank you. Okay? And as you can see in this picture, this block and this block, they cross. Okay? So I said that the partition is not crossing if I don't have this crossing in this picture, right? So a partition which is not crossing, for example, is this. Yeah. So in fact, what Roland realized was that the only difference between classical probability and free probability is changing the set of partitions to the set of non-crossing partitions. Okay. And in fact, here if you put the central limit theorem, you will have pair partitions, and then you will realize that the moments of the central limit theorem is just the number of pair partitions, which is the 2n factorial moment. Okay? But in free probability, this is an exercise. You can show that if you count the number of pair partitions, is counted by the Catalan number. And one thing which is interesting is that if you put the cumulants to be 1, 1, 1, 1, then the moments are of the Poisson are the same one, but forgetting about the odd ones. Okay, So there's a lot of combinatorics there, okay? And we will come back later to this framework, okay? But I want to talk, why would, if I am a probabilist, why would I care? So there is the most important example of applications of free probabilities from random matrices. And the idea is that here I need to talk about convergence in distribution or joint distribution. And for me, convergence in joint distribution means that the joint moments converge to the joint moments of the limiting distribution. Okay, and I say that two guys are asymptotically free if the joint moments of an and bn converge to the joint moments of a pair of abstract free random variables. Okay, and why do I care? Because Voiculescu showed in his seminal paper of '91 that if I had Gaussian matrices, then asymptotically they behave like free random variables. So I can calculate the joint distribution of, for example, the sum by going to the abstract framework and calculate the free convolution of these two guys. Also, and this is maybe more illustrating, is that if I have an and bn deterministic matrices and n is very large, then if I conjugate this guy with a unitary, meaning that I rotate randomly, then this guy and this guy will be asymptotically free. And the intuition, and this is maybe what you should get from this talk, is that the intuition is that somehow, if two random matrices are in random positions, one with respect to the other, somehow there is no relations. So you have, for each n, you have a matrix, for example, diagonal matrix, but also you assume that when n goes to infinity, they converge in distribution, meaning the empirical distribution converges. Was this clear? Yeah, so this is what I mean by deterministic matrices. So there is no randomness. This is just like my second example of non-commutative probability space. Okay, so I make them random by rotating them randomly. So I keep the eigenvalues, but I make the eigenspaces random. And if I make this, somehow all the relations, even I can take A and A, I can take the same one. And then if I rotate one of them, one of the copies, then they will be in free position asymptotically. So what can I do with this? Well, I can calculate many things. Of course, this is the semicircle law, which was proved by Wigner. This is the so-called Marchenko-Pastur, which is the square. But we can calculate, for example, this curve was calculated by free probability, or this curve here explicitly. And maybe one interesting example is the free commutator, because in classical probability this is 0. So this is one example you see really the non-commutative thing. And this curve was also calculated with free probability explicitly. This curve is calculated using not the free convolution, but something called the free commutator, and this is explicitly explicit. We know how to do this. Okay, and this is a random matrix which have big semicircle Wigner matrices. Okay, good. Okay, and for the general case for a polynomial, we don't have a formula, algebraic formula, but we can do iterative. So fixed point equations will give us approximations of this curve here, and these are two works, one about the operator valued free multiplicative convolution and one about operator valued free additive convolution, and they use this with another trick which is called the linearization trick to give answer to any polynomial. So we don't have a formula, we have a formula close enough, let's say. Okay, and so this red curve was calculated using free probability. Good. Okay. So how much time do I have? 20 minutes. Okay. So I will talk now about what is finite free convolution. So this is very, very new. And the idea is the following. So the classical approach, or the approach that I mentioned before, was the following. You take A and B, which are deterministic random matrices, size D by D. Then you consider A plus U, B, U star, where U is unitary with respect to the hard measure. Then what you do is you consider the expectation of traces of Xn, okay? And then you can find a measure such that this expectation of traces coincides with the nth moment. And this is exactly the average empirical distribution that I mentioned before. So the new approach is you take, again, A and B, D by D matrices. Again, you take, so this is an X to be A plus U B U. But instead of calculating the expected traces of X to the N, you look at the expected characteristic polynomial. Yeah? So this expected characteristic polynomial, you calculate really like the coefficients of the polynomial, right? And what you will get is here you get a measure which is possibly absolutely continuous. But here, the expected characteristic polynomial is a polynomial, so it has n roots, so d roots, and then you consider instead of this measure the measure supported at the roots of this polynomial. Okay, so this is new approach, and in fact. So again, you can take the characteristic polynomial, you take A and B, so you take P and Q, the characteristic polynomials of A and B, and then you look at the finite free additive convolution of P and Q is, in fact, the expected characteristic polynomial. Here you can take orthonormal, unitary, and most interesting, you can take also permutation matrices. Okay, and then you can prove that this doesn't depend on A and B, and so this defines a convolution on polynomials. So I have one polynomial, I have another polynomial, I can tell you another polynomial. Okay, so this is very, very different approach from the classical one. Okay, and in fact, what is very interesting is also that you can calculate explicitly this polynomial. So this polynomial, if this has these coefficients, then the convolution has these new coefficients. So this is very, very explicit. And the most important part is that if P and Q are real, because I want to stay self-adjoint. So this convolution is also real rooted. And the proof is they calculated this and then they realized that this was known since 100 years ago. And the advantage that many people have studied this convolution from the theory of polynomials. So there's a hope that this theory will shed a lot of light on free probability. Okay. I should also mention that there is an analog for multiplicative convolution, and in fact, you see this formula is even simpler. So the coefficients is just the product multiplied by some coefficients which do not depend on P and Q. Okay. So why do they care about this? Because they can prove by using this kind of inequalities that they can control somehow the roots of the convolution of P and Q. And they use this by giving some estimates on the R transform of free probability. Why do we care? Or why do people in free probability care? Because when D goes to infinity, because of concentration of measure, this finite free convolution approximates free convolution. And also this multiplicative finite free convolution approximates multiplicative convolution. So if I am able to say things about finite free convolution, I will also be able to say something about free convolution. Okay? And let me just mention, before I continue with cumulants, two papers from Marcus Spielman and Srivastava, who defined this finite free convolution, which are really impressive. One is about Ramanujan graphs, and this other one is where they prove these Gaddison-Singer problems. And really, they only used these interlacing polynomials to prove very, very strong results in two very different areas. Okay? So let me just quickly say what is finite free cumulants. So this is from my work with Daniel Perales, which is already published. So remember, I recall you what properties did I want from cumulants. First, I wanted to recover my cumulants from the moments. Second, I wanted that they behave nicely when I multiply by a constant. And third, and more important, they are additive. Okay? So here, we need to replace a little bit. So here, this is just a constant that is needed for the formulas to be nicer. But I can also put here just Kn to be a polynomial in the first 10 moments. Second is that I want to, if I multiply by a constant, it should go out by lambda to the n. And here, if I have a polynomial, what means to multiply by a constant? It just means that my roots are spread by lambda. Okay? One can give a very precise definition, but this is exactly what it should be. And finally, of course, that P and Q independent or finite free independent should satisfy that Kn of the convolution should be Kn of P plus Kn of Q. Okay? And what we did was say take the definition of the R transform of Marcus and do a la Voiculescu, take the coefficients of the R transform. And what we did was to say what is the combinatorial relation between the coefficients of this finite R transform and the moments. Okay? So definition is take the first d coefficients of the R transform. This is what we call the truncated R transform, and this will be the finite free cumulants of order D. Okay? So what we proved is that we have a very nice formula for the cumulants and moments, and vice versa from the for the moments and cumulants. Okay, and here I put it in this way because you see, how do we want to see this formula? What we want is to write a formula that is sum over partitions, and for each partition it should give me one coefficient. And the hard thing here is that this coefficient is not very nice. This coefficient is a sum of a Moebius function, and here d sub pi means the Pochhammer symbol. Okay? And if one wants to recover free cumulants, if the theory should go to the free probability in the limit, one should prove that this free cumulant converge to the finite free cumulants converge to the free cumulants to the free cumulants. Okay? And just property 1 and property 2 is trivially satisfied just because this is because of this formula. It's only a formula with the coefficients, some coefficients, but then I have here some over partitions on n. So this is homogeneous of order n, and you can look at the partition, at the complete partition, and you will see that here you will have mn. Okay. What we could also prove is that they satisfy this. This is a combinatorial argument. I won't make it. So somehow we can take cumulants directly from this definition and avoid the R transform. Second, how do we prove that they go to the free cumulants? The main step is to look at what is this coefficient. Okay, and if you can see here, the coefficient also has, in principle, terms of order higher than d to the n plus 1 minus sigma. Okay, so this is the main lemma to prove that they converge to free cumulants, is that this guy is a polynomial with leading coefficient this term and degree n plus 1 minus sigma. Okay, and let me just quickly explain how the proof goes that finite free cumulants go to cumulants. So basically we used this formula before, and now that we proved that this guy is of order n plus 1 minus sigma with coefficient the inverse of this, one can rewrite this formula as a monic polynomial, and then you see here the trick is how do I change a formula from partitions to non-crossing partitions? And I haven't seen this before, but this was a trick that Daniel showed me, and was that if I want to check any formula from partitions to non-crossing partitions, I just need to multiply exactly by the coefficient that was proved in the theorem. Okay? You see, if you have seen other proofs in random matrix theory, basically what you do is you take all the partitions, you divide in non-crossing partitions and crossing partitions, and you show that the crossing partitions go to 0. But here, this is very different phenomena. Okay, and this is just induction. Okay. Maybe just quick remark that we have a nicer combinatorial description of this polynomial, and this gives another moment cumulant formula. But somehow we haven't been able to use these combinatorial tools nicely to prove that in the limit this formula goes to the free cumulants. How much time do I have? Maybe 5 minutes. Okay, so let me just quickly explain some examples of applications. From this, we can recover what is the central limit theorem in this theory. Of course, we do the same proof because cumulants satisfy the same thing. So we just need to check what is the polynomial which has cumulants 0, 1, 0, 0, 0. And for this, we used a formula that we also proved, which is the relation between cumulants and the coefficients of my polynomial. And this gives me that the limiting distribution in the central limit theorem, it's in fact a Hermite polynomial. Okay. For the Poisson thing, I can do the same thing, and what I get is a Laguerre polynomial. So the Poisson limit theorem is a Laguerre one, and I just mentioned that it has an atom at 0, which is coherent with the fact that the free Poisson has an atom at 0 depending, and this is like the Marchenko-Pastur law. If I take m divided by n bigger than 1, then I have an atom at 0. Okay, so this is not surprising and it's coherent. Also, I can ask about what are the infinitely divisible distributions here. Surprise, there is only one. The only infinitely divisible polynomial with respect to finite free convolution, in fact, is this Hermite polynomial and constants, of course. So this was very surprising, but we could prove using these finite free cumulants. Second is Nick and Speicher proved that, in fact, for free probability, I can take any power, like any additive power, meaning that mu t, which has cumulants t times my original cumulants for t bigger than 1, is always a measure. So this is not the case for polynomial, but what we can prove is that for t large enough, this is a polynomial with real roots, and also that they are different. Okay, we have also a Berry-Essen theorem. So a Berry-Essen theorem here is, of course, with respect to the Hermite polynomial, and we can prove that if you take the n power, additive power, then you are with respect to the here we need to take the Levy distance because this is atomic. But with respect to the Levy distance, this is closer than 1 over the square root of n. Okay. Also, there's this thing which is true in free probability, which is failure or Kramer's theorem says that if I have two measures which add a Gaussian, each of them should be a Gaussian. And this is not true in free probability, but this is also not true even for finite free probability. And so you see many properties can be even proved at this level. Okay, let me just tell you finally some very recent work about spikes. So a spike in a random matrix is just like in the limit. Somehow you have all the eigenvalues are between -2 and 2, and you have one eigenvalue which is away from what we call the bulk. Okay, and one thing is that free probability cannot tell you anything about spikes in principle, because free probability only tells you about moments, and somehow it only tells you about the global behavior. But finite free probability can tell you, And this is something very recent that is work in progress. So what do? How do I get one spike? So I perturb my matrix. I add a rank 1 matrix, which has some eigenvalue outside of the spike. So what will happen is that, so this is like the characteristic polynomial of a rank 1 matrix, which I assume that all the eigenvalues are 0 but 1, which is at alpha. And what we can prove is that first that this polynomial and Q interlace, meaning that the roots are between the roots of the other one, but 1, and the other one is in fact between alpha minus 1 and alpha minus 1. Here I am assuming that the roots are in -1 to 1 just to take some normalization. And what it is very, very interesting is that how we prove this, and this was really just calculating things with polynomials, what we could prove is that the spike is in fact satisfying this formula, which is P prime over P equals 1 over lambda. And just this week when I was talking with Benai Georges, Roland, he told me this in fact we proved for random matrices, and in fact it's exactly the same formula that we got for the Cauchy transform. Okay, so we're getting somehow a very simple approach, which is giving the right answers. So thank you.
Is there any connection between this and E-freeness? Because I mean, E-freeness also takes care of this price.
I don't think, I don't know. I don't think that there is a strong connection between bifreeness and spikes. I think this is just. Infinitesimal freeness. Yeah, in fact, bifreeness, yeah. It's type bifreeness is how it's called. Okay, so in fact, it has some relation we're trying to understand, because here you see this P prime is because this guy Q is in fact is P plus alpha over D times P prime. That's why we have this equation. You want the roots of this polynomial? Well, you need to solve this equation. Okay, and if you look at this formula P plus P prime times some coefficient, what you obviously think about is about infinitesimal freeness. Infinitesimal freeness tells you I have my measure and I have a deviation which is derivative. Of course, this is very speculative because this is just formulas. But we're hoping to, in fact, have an interpretation about infinitesimal freeness.
And in this construction, you use the orthogonal matrices, right? You use the unitary group instead.
You can use orthogonal, unitary, or permutation. And this is very surprising that you get the same result.